Lecture 37 of Physics 72 discusses dispersion and polarization of light. They are found in subchapters 33.4 and 33.5 of University Physics. Please take time to read the objectives. It's mostly a qualitative discussion. You may pause the video if you wish. The first part of the lecture discusses dispersion. We tackle how the speed of light depends on the wavelength of the electromagnetic radiation and not just its material. We also gloss over how rainbows are formed from a combination of reflection, refraction, and dispersion. If you check the visible light spectrum, the color white is not included. This is because ordinary white light is a combination of colors. In terms of waves, it is a superposition of wavelengths throughout the whole spectrum. If you've played around the color functions in lots of computer programs, you'll see that the RGB function has white as being set to R, G, and B to 255. This is why you rarely see white lasers, as lasers tend to be monochromatic, or it follows a narrow range of wavelengths. While the speed of EM waves is constant in vacuum, it is not so when it travels in different mediums. We see that the wave speed and refractive index actually depends on wavelength, and this phenomenon is called dispersion. From the previous lecture, we note that wavelength and wave speed are dependent on the refractive index n. The diagram on the right is called a dispersion curve. It is an n versus lambda graphic that shows how different materials have different curves in how the refractive index varies as the color goes from purple to red. From Snell's law, we know that the amount of bending the light rays have depends on the index. If different colors will have different indices, then we are led to conclude that the light rays of different colors will not have the same direction upon hitting the boundary. These colors spread apart or disperse. This is most obvious in glass prisms. White light is shown on one side, as you can see here, with the incident ray not hitting the glass perpendicularly. This causes the white light to start splitting into different colors, and once it hits the glass air boundary again to leave the prism, here, the splitting becomes more pronounced. The amount of dispersion depends on how large the difference in N is between the opposite colors in the spectrum. So that means violet and red. Looking at the graph on the right, silicate flint glass has the most obvious dispersion, which is measured in angles. Some man-made materials exceed the dispersion capabilities of silicate flint glass. Diamond, for one, even though it's naturally occurring, has a relatively high difference in index of refractions for purple and red. This is why some diamonds tend to look polychromatic. With this, we achieve our first objective in relating dispersion to the color separation of white light traversing prisms. Let's answer some quick examples. If you were to ask which material has the slowest speed at violet light, we only need to remember that wave speed v is equal to lambda times f. This means that we look for the material that produces the shortest wavelength. Checking the formula for lambda, we note that wavelength shortens with increasing n. For this, the answer should be silicate flint glass with the largest index at refraction, because it has the largest index of refraction, at 400 nanometers. The second question asks us to determine the speed of a 700 nanometer light in vacuum traveling in a silicate crown glass. So to clarify, the 700 nanometer light is its wavelength in vacuum. And answering the problem requires us to use the dispersion curve for silicate crown glass. So from the plot, the n would be around 1.5 for that matter. So if we were to circle that part, it's going to be 700 nanometers. Sorry. So 700 nanometers would be around here. So it's around 1.5. Because of this, we can solve it by inputting it in the V equals C over N equation. This would be around 2 times 10 raised to the 8 meters per second. That's the wave speed. So with this, we complete the second objective in deducing the speed of light in a medium from its dispersion curve. The rainbows that we see are produced by a combination of reflection, refraction, and dispersion. We usually see them after it rains, and the water droplets in the air act as little prisms that do the work for these colors to show. If you're lucky, or observant enough, secondary rainbows show up with a larger arc and a reflected color scheme. We won't go to the specifics of how rainbows are formed, but it may be good for us to have a general idea. White light, coming from the sun, enters the water droplets, and will refract at different angles, as you can see here. The light rays get partially reflected at the back of the droplets, and will leave the droplet, eventually reaching your eyes in the famous ROY-GBIV fashion. These two refractions, the entry and the exit, disperse the colors. Double rainbows form from the light rays that reflect twice in the droplet. From here, the reverse order of the colors can be seen. There are actually multiple classifications of rainbows, and one can search them online if you are interested. In any case, the general principles of dispersion, refraction, and reflection are common for these rainbows to be formed. Let's answer a quick exercise. So here we consider the dispersion curve for a material shown in the figure. If light with wavelengths A, B, and C travel from the material into the vacuum, which of the following is the correct relationship between their speeds in vacuum? The hint is that we're looking for their speeds in vacuum and not in a specific material. So I'll give you a few seconds to think about it. So the answer is meant, or the question is meant to trick you. Recall that all electromagnetic waves travel at the same speed in vacuum. This means that A, B, and C should travel at the same speed C. The answer, or the correct answer, is letter D. We move on to the second part of the lecture, which discusses a concept that's been thrown around a bit in previous lectures: polarization. We see ways how we can clean or filter light according to the orientation of its electric field. Recall that from our lecture on electromagnetic waves that we studied a wave with a specific orientation. In our example, the electric field was chosen to oscillate in the y direction. Because of this, we said that the light is linearly polarized in the y direction. But what does it really mean when we polarize light? From what we know so far, polarization expresses the behavior of how the electric field oscillates. We also know that this is a characteristic of transverse waves, or EM waves. The question we have to answer is, what does it mean when it comes to light? How does polarized light differ from unpolarized light? Let's first go through an example of unpolarized electromagnetic waves. In general, the electric and magnetic fields of EM waves are not exclusively oscillating in just the y or z axis. Actually, they can choose to be aligned at an angle from y and z. That's of course if it's traveling in the x direction. More than that, there can be more than one E and B pair. Since they're waves, we can just use the principle of superposition so that the waves would be added to one another. If a single oscillating particle can produce a wave that's polarized in one direction, multiple molecules oscillating, such as in an incandescent light bulb, can have waves polarized in multiple directions. This means that the light emitted by an incandescent light bulb has no dominant polarization. One can say that this light is unpolarized or not polarized. In terms of electric fields, they could be oriented in all possible directions. We can say that the orientation is random. Unpolarized light is also called natural light because this is how electromagnetic waves are normally propagated without artificial intervention. Polarized electromagnetic waves, on the other hand, enforce that the obvious oscillation of E follows a particular pattern. An example of this would be waves emitted by radio transmitters. The vertical antennas used to broadcast these waves dictate the direction at which the waves would be transmitted. The receivers of these waves have better absorbing capabilities if the shape of their antennas match the type of polarization. This is why older antennas can be shaped straight, which indicates linear polarization, or circular, which can indicate circular polarization. In nature, you'd more often encounter light as unpolarized than polarized. The radiation coming from the sun is unpolarized, where the orientation of each oscillation is random. If you want to polarize or filter this wave, one can just block off all the other unwanted oscillations. We can do so by using polarizing filters. Unpolarized light that passes through filters eventually end up linearly polarized along its axis, or its polarizing axis. Filters usually have parallel insulating wires or grills that block waves that are polarized perpendicular to your desired result. Consider this filter on the right, commonly called a Polaroid. The Polaroid on the right is linearly polarized in the vertical direction, so its polarizing axis is vertical. Okay? This means that the resulting polarization of the light wave it spits out is linearly polarized vertically. Looking at the filter, it has insulating wires horizontally oriented. Waves that oscillate horizontally get absorbed by these wires, having their amplitude greatly reduced by energy dissipation. Waves that oscillate vertically remain mostly unaffected and pass through with little resistance. The light that exits the filter becomes vertically polarized as intended. Polaroid filters transmit at least 80% of the intensity of a wave that is polarized parallel to its axis, but at most 1% for waves polarized perpendicular to its axis. Ideal polarizers transmit all of the intensity of the waves polarized parallel to its axis, but completely blocks all the waves that are perpendicular to it. Ideal polarizers are unattainable in practice, but it does well in explaining the basics of polarization. Consider one ideal polarizer in this figure. Incident light, or incident unpolarized light of intensity I0 enters the polarizing filter, which has its polarizing axis at some angle not necessarily vertical or horizontal. Upon passing through the filter, we see light that is polarized parallel to the polarization axis. So in this case, it would be the polarizing axis would be this one, and then the light that it spits out is parallel to it. So it basically filters all of the perpendicular components. And the intensity of the light that's coming after the polarizer has its intensity half of what it was initially, so it's I0 over 2. So how has it come to this? Well, we can think of it this way. The electric field of the incident wave may be split to two components, one that is parallel and one that is perpendicular to the filter's polarization axis. Since the incident unpolarized light is a random mixture of polarization of all states, the parallel and perpendicular components are, on average, equal intensities. Since the polarizing filter effectively transmits only the parallel components to the axis, around half of the incident intensity is transmitted. We can widen our control of polarization by using more polarizers. So say that the incident light is already polarized, or that it has already passed through an initial polarizer. We can let it pass through another polarizer called the analyzer. Does it make sense that we just divide the intensity by half again? So consider the intensity of the unpolarized light to be I0. After passing through the first polarizer, its intensity would be halved, similar to the previous slide. Our question would then be, what would the intensity of the light be after passing through the second polarizer, or the analyzer? Or in another way of saying it is, what will be the intensity of the light at point P? The intensity is dictated by Malus' law, which states that the intensity of the light after passing through two polarizers is given by I is equal to I max cosine squared phi, with phi as the angle between the polarization axis of the two polarizers. So why is cosine squared? That would be the next question. Consider the electric field after passing through the first polarizer to be E. We can decompose its vector according to the sine and cosine of phi. Upon passing through the analyzer, only the parallel component, or cosine phi component, of the electric field will remain, since the perpendicular component will be absorbed. Unfortunately, we have skipped the discussion relating intensity of an electromagnetic wave to its constituent fields. The intensity is determined from the square of the electric field, so the cosine would be squared as well. Malus' law will only make sense if the incident light passing through the analyzer is already polarized. Here's an example of an analyzer being rotated so its polarization axis will change, or effectively changing phi. There is already one polarizer behind the lens, so notice that the light through the polarizer is already a bit darker than the rest of the image's background. This is due to the first polarizer cutting the intensity of the light by half, and allowing the light coming to the analyzer to be already linearly polarized. So at this point, let's time the right time, the instant at which the polarizing light or the polarized light is at its maximum. So when he rotates it to the right, it turns black, and when it rotates the axis maybe towards the top, it's going to be at its maximum value. But even at its maximum value, the light will be slightly darker than the background light. So by rotating the analyzer, we see that the angular dependence of the light intensity is in action, with the light becoming completely dark at some angles. So at that angle, phi is equal to 90, or that the axis, the polarization axis, would be perpendicular. So to clarify something that may be a bit confusing with the equation from Malus' law, I max is the intensity of the polarized light and not the polarized light. So this would mean that this is I max, this 0.5 I naught. Okay, so it's given by 0.5 times I naught. Here's a summary slide for the mechanism for two polarizers working side by side in Malus' law. You may pause the video if you wish. With this, we accomplish the objective of using Malus' law to determine intensities of light transmitted through polarizers. Here's an example to help our understanding. Unpolarized light with intensity I naught is incident on two polarizing filters. The axis of the first filter makes an angle of 60 degrees with the vertical, and the axis of the second filter is horizontal. What is the intensity of the light after it has passed through the second filter? Looking at the bit at the given, we know that the angle between polarizing axes is 30 degrees, because the axis of the first filter makes an angle 60 degrees with the vertical. For the second filter, it's 90 degrees, because it's horizontal. So the difference between the two angles is 30 degrees. This would mean that cosine squared 30 is basically the square root of 3 over 2, or 3/4. But since the original intensity I naught is halved upon passing through the first polarizer, we have to add 1/2 as an additional factor. The intensity, after passing through two polarizers, is 3 I naught divided by 8. Let's answer a second example. Light of original intensity I naught passes through two ideal polarizing filters, having their axis oriented as shown below. You want to adjust the angle phi so that the intensity at point P is equal to I naught over 10. So it splits the two questions. If the original light is unpolarized, what should phi be? And the second question, if the original light is linearly polarized in the same direction as the polarizing axis of the first polarizer the light reaches, what should phi be? To answer both questions, you only need to isolate phi from Malus' law. So what we have to do is, well, that's the answer already. What we have to do is first get cosine squared phi is equal to the ratio of I over I max. And then to get cosine phi, just take the square root of I over I max. And then finally, phi is just equal to the arc cosine, or cosine inverse, of the square root of I over I max. Sorry for the handwriting. So all that's left for us is actually to determine I over I max. We know that I max is the intensity of the light between the polarizer and the analyzer. For the first instance, I max would just be I naught over 2, just like our previous examples. So that should mean that the answer is arc cosine 1 over square root of 5 after you input I over I max. For the second example, the original light is already polarized in the same direction as the axis of the first polarizer. So I max would just be I naught. Because of this, the answer is arc cosine 1 over square root of 10. The quiz asks us for the intensities of light at points A, B, and C in terms of the original intensity I naught of the unpolarized source. You may pause to have enough time to think. So at this point, determining the intensity of A should be pretty obvious. It's just I naught over 2. For B, the angle between the first and second polarization axes is 60 degrees. So cosine squared phi is just 1/4. The intensity at B is then I naught over 8. And to answer C, we use I max as the intensity coming from B. The angle between the axis of the second and the third polarizer is 30 degrees. So all we need to do is multiply a factor of 3/8 from B, as with the previous example, or the very first quiz we had. The answer for C should then be 3 over 64 times I naught. While this is not part of the objective, there are other ways to polarize light. One other method, is by reflecting light at a specific angle dictated by Brewster's law. The reflected light is linearly polarized when incident light strikes the surface at a specific angle theta sub p. This angle is dependent on the ratios of refractive indices of the material, so it's similar to the total internal reflection. Here is a summary of how light may be polarized via reflection. You may pause the video to check the quick summary. And to end the lecture, so far we've only considered linearly polarized light. The last few slides will breeze through how else light may be polarized. We can produce a circularly polarized light beam if we add two sine waves of equal amplitude that are polarized in the y or z directions, if the electromagnetic waves will propagate in x. And the phases of these two waves should be a quarter of a cycle apart. For our example, our wave oscillates circularly in a clockwise fashion, making this a right circularly polarized wave. If the wave cycles counterclockwise, we get a left circularly polarized wave. If the waves superimposed are not in equal amplitudes, or if their phase differences are not a quarter of a cycle apart, the circular polarization becomes distorted, and an elliptically polarized light is formed. With this, we complete the last objective in differentiating the types of polarization. This is it for lecture 37. Thank you for listening.